This meeting.
Again, welcome to today is November 17th. This is actually the week before the Thanksgiving break. So next week there will be no school. So we have quite a few content to basically cover, and I'm hoping that you guys will do these things. There was actually a couple of assignments also that were posted today, so I'm hoping that you guys would have also received notifications about those. And they are actually have to do with the quiz and also another assignment for the homework related to basically problem solving. So I'm hoping that you guys have noticed that and you take care of these things. They are not due actually next week because next week there is no instruction. They are due immediately after next week. Typically, usually the assignments are due around the end of the week, except this time because we're skipping 1 week due to the holiday. The assignment is going to be due actually on Monday, 11 p.m. So I really want you guys to make sure you pay attention to this dates and when things are due. So that is item number 1. And then, like I said, we have quite a few content to cover. So I'm going to start on it right away, unless you guys have any question. And I see that there are a lot of people who are not here. Apparently, they are deciding to take the holiday early. Okay. So let me share with you the content if I can ever find it. Yes, it's this one. So today the topics are basically, I think there is an issue with the title initially, and I fixed it. Okay, I fixed it at least in the discussion basically, and actually the summary. So the topics are actually going to be on light waves and basically from a classical perspective and how we actually learned that light is actually a wave, running those experiments of Mr. Young and other people around him and around the toward the end of the 18th century, the beginning of the 19th century, the late 1770s, 1780s, and then basically the early 1800s. That's the timeline when we discovered actually that we could prove actually experimentally that light was a wave. We didn't know then what was waving, but we knew it was definitely waving. So here is in a nutshell what we started with. We started with the hypothesis that light is made of tiny particle because when it hits interface, it's going to bounce just like when you throw a ball on a wall, it's going to bounce back, and it's going to bounce back following the laws of reflection. And also it's going to refract because its speed basically slows down in the media. So that's the particles of light as they hit the medium, basically the separation, they slow down. So we went from the idea that light is actually a particle made up of tiny particles going in a stream basically from the source all the way to where they bounce off. That explains perfectly the laws of reflection and refraction. This is geometrical optics. Okay. Then we started to suspect that there are other experiments actually that show light is actually a wave. Mr. Young's experiments and what we're going to discover today in terms of the phenomenon of diffraction, in terms of the phenomenon of interference to this the double slit experiment, in terms of the interference due to the single slit experiment, and in terms of also multiple slits where, like for example, diffraction grating, all of them prove and show without a shadow of the doubt that light actually is not particles as we thought initially it was, namely the fact that the laws of reflection and refraction obey based on the idea that it's a particle, but rather it is a wave. We didn't know what it was waving, but we knew it was a wave. That was early in the 1800s. Toward the end of the 1800s, there was famous experiments and also the theory of Mr. Maxwell that shows actually that not only that it's a wave, but we knew exactly what was waving. It was the electric field and the magnetic field as they're basically following the laws of Ampere and the laws of Faraday and the laws of all of these laws, basically mutually creating each other, and they're propagating in another direction. So we knew it was a wave. We were able to find its speed, namely the speed of light, and we were able to find its frequency. We were able to find its wavelength. And that supports the experiments of Mr. Young. So Mr. Huygens actually came up with, before that, actually came up with the principle that explains the phenomenon of diffraction and interference and all of these things. And in addition to that, actually you can deduce also the laws of reflection and refraction. So we were happy that light is a wave. Then comes in experiments with the photoelectric effect, which we're going to discover later on. So basically you shine a light on a metal, and that light, as it hits the metal, it extracts electrons. Just like the photocells that you see on some of the houses now that they have electric, they generate their own electric power. That could not be explained by the light being wave. It has to be particles. Okay. So, and Mr. Einstein, actually, the reason why he won the Nobel Prize is because of this. He was able to explain the photoelectric effect using the idea that light is made up of tiny particles. Later on, we call them photons that make up light. So light seems to be perfectly within every single experiment that you conduct a wave. Light also seems to be, with every single experiment that you conduct, also being a particle. So what is it? Is it a particle or is it a wave? The answer is going to be in the next few chapters, where light is actually a particle, solid object with like a particle, like mass and everything else, but a wave also, which is not a particle. So it's this and that in the same time. This principle of duality, we're going to talk about it later on, and it's not actually for light too that exhibit this phenomenon. Also, electrons also, they can behave at times as waves, and they can behave at times as particles. And since we mentioned electrons, actually the proton, everything else also is actually can have this duality. To some extent, some of these aspects are extremely negligible in some objects than others, but every single object has this duality, has this dual behavior. Okay. So this is basically where we started from, around to the 1600s, where Mr. Newton and everybody else were experimenting with the laws of reflection. So we were happy with the fact that light was a particle. Then we abandoned that idea with Mr. Huygens' principle to explain the phenomenon that needed the particle nature of light, and also to explain the fact that it was waving. Mr. Maxwell and his work showed that without shadow of the doubt that it was actually a wave. So we were happy at that point. Then came the idea of Mr. Newton, Mr. Einstein, that actually showed that light is actually a particle back to the starting point. So it's really, that's how the idea evolved. Now we know that light is actually both. Okay. Light is actually has this dual behavior. So this is in a nutshell where we are right now in terms of the thinking and in terms of the history of the object, the topic, and things like that. So Huygens' principle, we're going to start with it. It's really it reiterates the idea of wave nature. I know that there are some experiment, or at least some things in the book, trying to explain some sort of experiments to show that it's that some sort of the principle is valid, and it is valid because of its consequences, because it works, it leads to tangible results which are true. However, it's not like Newton's law of motion, for example, F = ma, which we can prove it by finding a way of measuring the force, by finding an independent way of measuring the mass, by finding an independent way of measuring the acceleration. Multiply these two quantities at any experiment, and we always find them equal to the quantity of the force. So that is a law, because you can do it time and time again under any place, and it's always going to work to give you F = ma. So that is a law, meaning it will never be broken. It cannot be broken, at least within the context of classical mechanics. A principle, on the other hand, is something that usually you have difficulty in proving. You cannot really, there are some things that might not be 100% accurate about it, yet it works. It yields results. Sometimes you even have suspicion that it should not work, it should not be correct. That's what the principle should say. A principle is something that you have some arguments in it that are flawed. Okay, but the results of it are impeccable. They're as good as law. They are perfect in a sense. As long as you apply it within that that idea, they are perfect. So it did not reach the level of a law, but it's almost there. So that's the idea of the principle, so that we have a distinction between the 2 points in here. So we're going to discuss that. There is also a Fermat principle, which we discussed a long time ago when we did the geometrical optics, and that actually is a principle also, in a sense that we say that light, in going from point A to point B, takes the least time, okay? Not the shortest distance, the shortest time. Okay, so that's a principle, and we're able to discover, actually, based on that, the laws of reflection and refraction. So it works, okay? What is the proof of it? We don't know how that light is going to, I mean, to put it in terms of the words of Mr. Feynman, when he was discussing this very same point, he was saying, okay, is it then the tiny particles of light? Do they have with them calculators, and they're calculating the path to see which one is the shortest distance? So they know that they're going from this point to that point, and every single point where they're at in time, doesn't matter. They're in the beginning, just immediately after they started, right, almost in the middle, wherever they are, they have to figure out, they have to do some math actually to figure out the least time path. So they have to do an infinite number of paths and see which one is the least time to continue to the next step. So that seems to be the thinking, if that's true. But again, if you try to think a lot about this thing, sometimes it gets a little bit confusing. And the principle, like I said, is taken for its face value as is, because it leads to an answer, it leads to a result which agrees with the experiment. And like a law, which itself is provable. You can prove it in the lab day in, day out. So that is a law, okay? So that's the thing I was going to mention today about this thing. And of course, the topic of the discussion today is going to be an Huygens principle. You're going to state, so that's question number 1 for the discussion today. You're going to put it in your own words, okay? Please do not copy and paste, okay? You're going to see the principle. You're going to learn the principle. I'm going to try to explain it to you. You can go to the book and look at it. You can read it. You can Google it. You can go to, what is it, Wikipedia. You can go to wherever your reference is, but try to put it in your own terms, okay? So Huygens principle. So that is item number 1. Do I have everybody on board? At least the ones who are here? Okay, very good. Josh at least is on board. Anybody else? Okay, at least I have a couple of people now. That's good. Okay. I hope the rest of you also are going to do the same, okay? So, then we're going to learn about the laws of diffraction, the principle of superposition also. This is not a principle really when it comes to this thing. It's more like a law. The reason why I'm saying it's a law is because you can prove it mathematically for the case of waves. Waves, they obey something in math called the wave equation. And the wave equation is actually a linear equation, and you can prove mathematically that the superposition works in this case. So it's not a principle in a sense, it's more like a law, okay, that you can prove mathematically. And that leads to interference. So you have wave 1 and wave 2, and they're coming together. And when they meet, where they meet, they produce a signature behavior of waves, namely interference patterns, okay? 2 waves that come on phase, and their amplitudes are high, the combined amplitude will be the sum of the 2 amplitudes, okay? And if they come out of phase and they have the same amplitude, actually they will cancel each other completely. And whatever phase they come in, they will add up accordingly, okay? Particles do not do that. Particles, if I have this ball and this object, I cannot make them so that I have now somehow a new object that is somehow bigger of the 2. So particles do not interfere. Particles, they either hit one another, bounce off each other, or skip one another completely. But waves, they seem to combine into a new wave, completely new identity, and this identity is actually has its own characteristics, has its own amplitude, and it's distinguishable from the individual components. Okay, so that is what interference is. Then we're going to talk about polarization, and I think we talked about it when we did the electric field and so on and so forth. The fact that it has to do with the orientation of the electric field. And again, you have polarizers. I think I have a few of them. I don't know if I can grab them or not. Let me get this tripod out of the way. See if I can grab them later on, because they're on the other side. And they filter basically the light depending on the specific wavelength, the specific direction of the electric field. Okay, so if you can take a polarizer going in this direction and another polarizer going in the other direction, you can cancel the light completely. Okay, and once you polarize it in one direction, statistically speaking, that's 50% of the light in that direction. The other 50% is canceled, because again, all you're doing is singling out the direction of the electric field. That's all. So, and you can direct it in such a way that it doesn't, so in the evening, for example, or in the morning when you're driving, there's too much light coming in all directions, and that is going to give you all directions, and the light is diffused in front of you, and you cannot see very well. But if you have polarizers, or polarizing glasses for driving, then what they do, they will cancel all the other directions, and they will keep one direction and give you a clear picture of what's going on in front of you. Holography is another thing that is actually interested now, especially with the advent of virtual reality, basically technology, and also with the advent of enhanced or extended basically reality, also especially in terms of gaming, but also it's used in other fields, like for example medicine and other fields that are incoming, for example for down the road technologies, for example for exploring things, and maybe even experimental research or other things too. Okay, where you could do applications with this one. So again, holography is a combination of the colors to give you the different the depth basically perception, so that you will see 3D objects, okay, or interact with 3D objects. Okay. Then we're going to talk about the emission of light. Okay, you have an object that is excited, and once it's excited, basically you raise its temperature, for example, you heat it up. Okay. At that point, every single element or every single compound has its own unique signature, because once it's excited, it wants to go back its own to its ground state when it's basically releasing energy, and those are those spectra that it emits. The light that is going to emit is going to be specifically dependent on the properties of that element that is in there. This is as opposed to the absorption spectrum, where you have, for example, a material in here, and you have an incoming light going through it, or an incoming beam of light going through it. Then the material will absorb that, is excited now by the light, and the spectrum on the other side will show missing light. Okay, so the emission spectrum is the presence of certain frequencies, and the absorption spectrum is the omission of certain frequencies. Okay. And the emission spectrum for specific elements is the inverse of its own absorption. Okay, so if you look at it, for example, the spectrum for a specific material, when it's emitting, you're going to see lines. Okay, when it's absorbing, you're going to see everything, but those lines are missing. So that's basically in a nutshell. Then we'll talk about the phenomena of fluorescence and phosphorescence, and then we'll talk about lamps and lasers at the end. So this is in a nutshell your chapter, or your two chapters actually. And they're not much, they're not really that much, especially the next two chapters are not even that much, relatively speaking. Any questions? I know some of you are sitting in Physics 11, and we did just an experiment on these things related to the laws of diffraction and actually interference and things like that, and the double slit and all of this. So I'm hoping that this will catch you, at least you'll be caught up with the lab. And if not, actually you have a head start on the this content for the lecture. Okay. So again, when you throw a rock on the ocean or in the surface of the water, you see the wave patterns that form. Okay. So what you have in this case is what you will see. You see wave fronts, and those wave fronts, they spread. Okay. to help us understand how this works, Huygens principle can be used in here, because you only have this one source of disturbance that happened right somewhere in the medium. But how in the world that same disturbance now is seen somewhere else? Okay, now it's seen in here. I have seen a wave front in here, but the next, depending on the speed of the wave, the next time I will see it in here with the other wave front in here and with another one behind it that is forming, and so on and so forth. So again, what I mean by wavefront is actually that spreading. Okay, for example, look at the maximum, the peaks. That is what I mean by the wavefront. If you don't like the peak, for example, you like the trough, that's fine. Look at the trough. If you don't like the trough where the wave, that's fine. Any point in there can be considered as wavefront. Typically, we talk about the maxima in this case, okay, where it's oscillating at its own maximum, which is the height in this case. So here is the principle. Remember, this is your assignment today. Please do not copy this and paste it. That is not the intent of it. I want to see understanding. I want you guys to understand exactly what this means. So here is verbatim. Every point of a wavefront, this is a wavefront, A, okay, may be considered the source of secondary wavelets. So every single point in it. I want to ask you a question. How many points between 2 points? If I take this point in space and this point in space, how many points there are between them? You're right, Kai. So there is an infinite point, okay? So very good, Kai. So think about this. Every single point that you draw, even if as close as they are, and you think, okay, I reached now, this is the extent of the pen or the pencil. It cannot draw another point in between them. How many points in between those two? An infinite number of points, just because your pen is too thick. That's the problem with it. If you can invent a pen that has a smaller, basically, writing capability, is going to draw an infinite number of points, not just another point. So that is the idea in here. So every single point on a wavefront, which of course is not just these points that are drawn in here with the red dots in here. Between this one and this one, there is an infinite number of them. So you have to think that there is always many of them in here. Again, that is a difficulty of having to prove that. That is the flaw, if you wish, that you're going to argue in terms of a principle. Because how am I going to come up with all of these points to really make sure that it's working? Okay, in order for this statement to be proved, I have to come up with every single point, and I cannot draw every single point, because just between these 2 points, I'll have to spend an infinite amount of time if I want to count just the number between them. As a matter of fact, once I find the next point, let's say, for example, this one, between this one, there is an infinite task. Between this one and the other one, there is an infinite task. So conceptually, it's a little bit difficult to construct, okay, because of this statement. But it works. That's the whole idea of it. So if you can be happy with 10 points, good. Then you can draw it perfectly. If 10 points are not good enough for you because it's not accurate, okay, draw 20. If you meet the satisfaction and you see the graph working, great. If 20 is not good for you because somehow you have some waves that are not exactly like the initial wavefront because it's too broad, for example, and the wavefront is so big and 20 is not enough, draw 40. If you're not too happy with 40, draw 80. Draw 1,000,000, as a matter of fact, okay? Ultimately, the idea in here, you will reach it. How can I prove that? Well, it works. That's the whole point of it. Does everybody understand the slight distinction here between what the principle is and what a law is? A law is perfect. Law, you can prove it. Okay, very good. So every point of a wavefront may be considered the source of a secondary wavelet that's spread out in all directions with a speed equal to the speed of propagation of the waves. Now, if you really draw an infinite number of points, and the new points, once you reach, for example, a certain distance, after 1 second, for example, which is going to be a V in this case, If it's an infinite number, all of them, they will meet in the new wavefront. So the new wavefront will be the envelope of all of these wavelets. So that is your new wavefront. So the wavefront would have moved if it is 1 second. If it's less half a second, for example, that you decide to draw this thing, it's going to be V/2. Okay? If it is 5 seconds, it's going to be 5 times V, the separation between the two wavefronts. So again, how far I'm going to draw them, that depends on you. Okay? The longer you wait, the more points you're going to need to really draw the wavefront correctly. Obviously, this is the principle, and the idea behind it actually is not even to draw these things. It's not, the point is not to draw this wavefront to show this thing. It's just the principle, because it's going to help us in the theory later on. Okay, so I think I talked a lot about this principle, and I'm hoping that you guys have, at least from my perspective, a lot of things that I said about it. The task again is you guys, you think about this principle and you put it in your own words. Do not copy and paste. Put it in your own words, okay? How you think of it. Okay, so that's task number 1. Let me write it down, at least for those who are here, so that they can understand what the task is. Put Huygens principle in your own words. Again, this is the point, okay? It really works when you can see it clearly when you have, for example, the opening in here that is small enough, and you create a disturbance behind it, and you see this wavelets forming in here. So, and there is a relationship now between how much the opening is and the wavelength. If the wavelength in here is comparable or greater than this opening, then you're going to see this wavelets. If the opening actually is much bigger than the wavelength, you're probably not going to notice it. You're going to see nothing in here in terms of that. Which brings me to this idea of waves. If you really want to see a wave, you really have to have sizes comparable to the wavelengths. That's why we missed it all along. That's why up until the 1800s, we didn't see the waves. I mean, if we could see sizes of the order of a micrometer, if we could see sizes of 100th of a micrometer, we will see the light actually going up and down. Okay, we will see the wavelengths, the waves of light waving. But because we can't see that small distances, we did not have any experiment to experiment with those tiny sizes. Therefore, we missed this point completely. Okay, that is really the issue that we have in here. Until Young and everybody else came up with these experiments where they have openings very small, and they shine on it different colors of light, red and green and all of that. Then they see the phenomena of interference now develop before their eyes. They see the wave nature of light. Okay, so that is really the idea behind it too. And it's illustrated in this example. You see clearly diffraction in here. You can clearly see the waves in here going in this. I mean, they came straight out. If there was no, if it's not wave, they could have come out straight out. But now they're spreading. Okay, so they are diffused in this case, going around the edges, and that is because they are waves. Okay. If sound, for example, was not a wave, you would not hear people on the other side, basically, when they're talking. Because if sound is just a particle, it hits the door and bounces back. But because sound is actually a wave, it's going to be transmitted, and you're going to hear it on the other side. Okay? Again, waves Again, this is because we are looking at an object of a smaller size. So wave now will create this goes around the object in here, at least on the small distances, okay? And that is actually how the shadows actually are formed too, okay? If the opening is super wide, you're going to have the shadow will be fine, okay, if the object to the light in here. But if the shadow is the opening is very small, then in this case there is a spreading of light, which makes it there is a diffusion in this case. This is the point I was trying to illustrate earlier, okay? So the amount of diffraction in this case, basically, sorry about that. Sorry about that, guys. I don't know why the internet sometimes does this. Sharon, yes, I'm here. Did everybody hear me okay now? Okay, thank you, Sharon. Thank you, Kyle, and everybody. Okay, so let's go into the. So we probably have to expedite this thing to make sure that we don't have this problem again. So again, if the wavelength now is basically can circumvent this object, it can go around it in here. Okay, so again, this is the point that I was illustrating in here for the shadows. If the opening is wide in here, in this case, you will have a sharp image of the object. Now, if it's small like this one in here, that's where you see the diffusion in here forming, the fuzziness, if you wish. Again, the object that are of the same size of the wavelength will always produce this blurriness. So in this case, if you're going to focus an object, you have to really basically make it either bigger or come up with a different wavelength. Okay, here is a point that I was talking about earlier in terms of the principle of superposition. If you have two waves, in this case, we have a wave where it has its maxima here, and the second wave that has this maxima occurring in the same time. So these two waves are in sync, okay? They reach their maxima at the same time. They vanish at the same time, and they reach their minima at the same time. When you add them up, like I was showing earlier, with the particles, you can do that. When you add waves, now you produce a new wave that has a much bigger maximum than either. And it's distinct. I mean, you cannot distinguish the two waves in it. You cannot see, for example, in here, I cannot fool you to tell you, hey, which way the white ball is. You can always see it, but with waves you can't while they're interfering. You cannot see where one wave starts and the other one ends. So when they combine, they combine. You cannot do that. Now, if they are out of phase, in this case, they are out of phase. When the first one is at its maximum, the other one is its minimum. When the other one is its minimum, the second one is its maximum. When they add up in this case, they cancel. If the two maxima are the same, if they have the same amplitude, they will actually, you cannot see the wave at all. You wouldn't think that you have a wave. Imagine these two particles, they come in here, and some point they will completely disappear. Okay, that would be like magic. Okay, that's what's going on with waves. This is a signature of a wave. If you see interference like this, you know 100% you're dealing with a wave. Particles do not do that. So when we were thinking that light was a particle, that's fine. We could explain the law of reflection and refraction. But the minute we discovered that light interferes and patterns of bright spots form and dark spots form, because the dark spots there is cancellation, and the bright spot because there is actually a reinforcement. So in this case, we knew that light is not a particle. It must be a wave because of that experiment. Because interference is a signature of waves, okay, in general, not just for light in this case. Okay? Does everybody understand the point in here? By the way, this is true not just for light, for any kind of waves too. This is, for example, on the surface of water. The surface of water is not a one-dimensional surface like this one in here, a one-dimensional object. The wave patterns are clearly distinct in this case, of course. You have these areas in here that extend, and this is basically what we mean by a wave pattern, by an interference pattern that forms because of these interactions in here. So the overlap in here is a signature of waves. Now, how much, where the overlap happens, depends, of course, on the separation of the sources, depends on the wavelengths of the sources, and so on and so forth, okay? It depends on where you are looking at them. So think about it this way. Let me stop sharing the screen in here and share with you, okay, hold on, and share with you this screen. Imagine yourself living near the ocean, okay? So you're on a boat, okay? You have some people that I heard of living on boats, okay? At least. So you have a boat in here, and this is ducked in here, and you have your friends and so forth. And on this side, you have the ocean waves. This is the ocean waves, but you have an opening in here. As the waves start to come in here from the ocean, of course, they're going to go through this opening. This is typical of basically near the beaches where they have these things. And there are points in here where the intensity of the wave will be amplified, meaning the wave will be higher than even the wave that started in here. Okay? There are points in here that are very calm. So depending on where you move your boat back and forth in here in this location, knowing the distance in here from here to here, knowing this opening, how much it is, knowing the wavelength, basically the distance between every two crests from the ocean, you can determine the safest place for you to continue with your party. Of course, we can do parties now though because of Corona. But if we were going to do it, you can find a place where you and your friends can basically hang out without having to be disturbed with the waves. And there are points on the same location in here where actually the waves are going to be worse than being in here. So this is, again, property of waves, okay? This is difficult to do, by the way, because the opening has to be specific, because it's actually difficult to distinguish for a single opening. When you have two openings, where it's actually going to be easier, okay? This is actually in here where I have two sources, but even with one source can produce those, at least not one source for opening, it's called a slit, okay? Again, now, so when you have two lights coming from two different points, and if the two maxima happen to be in the same time, you have a bright area in this case, okay? Bright fringe is called, okay? It's called a bright fringe. And where they cancel, you have a dark fringe. Because the maximum of one comes with the minimum of the other, and there is total cancellation in that point, if they have the same amplitude. Okay? Usually the experiments are arranged in such a way that they have the same amplitude. Because if they're not the same amplitude, you will never have dark fringes. You will have low light, low intensity fringes, and high intensity fringes. Did I misspell this thing in here? I'm missing the E. Okay, so we have constructive and destructive interference. Those are the 2 points that we have in here. So again, we shine a light, a monochromatic light. The key word in here is monochromatic. It has to be the same wavelength. That is what monochromatic means, same color, which means same wavelength, same frequency. And you shine it on a surface, and you basically, in this case, you have 2 openings called slits. Okay, this is the double slit experiment. And what happened in this case, if there was no interference, if light was not a wave, this is what you should have seen. You should have seen a big intensity near the first slit and another one next to the second one, and that's the end of it. So basically, you probably will see something like this, super bright in here, a little dim in between, and another bright region because it's coming from 2 spots, and that's it. But you don't see this at all. You see actually this repetition of dark fringes with bright fringes, dark fringes. Between every 2 dark fringes, there is a bright fringe, and between every 2 bright fringes, there is a dark fringe. So this is the typical behavior of a wave. That means that I am seeing constructive and destructive interference per this relationship. Okay, so where in the middle, usually it's always, not usually, it's always bright. Then you go up one side, you're gonna find a dark spot where there is complete destructive interference, and then there is a bright spot in here, followed by another dark spot in here, followed by another brighter spot in here. How far can it extend? Depending on this distance, okay, and this distance actually between the 2 slits, okay, depending on this distance between the 2 slits. That's it. And of course, how far you are from them. So this is the plate. This is your where the 2 slits are, okay? And that determines everything, okay? Just by measuring this distance from here to here, we can determine what the wavelength is. If I know this distance and if I know this separation, I'm in business. We can find exactly what's the wavelength of the thing that is waving. So this is basically the double slit experiment. By the way, there is a lot of talk about it in philosophy nowadays, especially because of the fact that it has to do with the multi-universe and all of that. So if you're into, this is not sci-fi, by the way, this is really science, okay? Whether or not we live in a single universe or in different universes and all of that. So there is a lot of discussion. It all relies on this idea, the double slit experiment, okay? Of course, when Mr. Young did it in the early 1800s, he has nothing to do with this discussion. It came later, actually, in the 1920s, 1926, 27, when we repeated it for the electrons with the same experiment, but instead of shining light, we shined electrons. That's when also they exhibited the same thing. And so that made people suspicious into whether or not we live in a single, basically, in a universe with one basically options in it, or we are living in a multiverse where all the options are available, and this is the idea behind it. And until now, this issue is not resolved in science, by the way. This is not sci-fi, this is science, okay? It's all related to this one. So if you're into philosophy or even theoretical physics, there is a lot of discussions about this same thing in there. Did anybody hear about the double slit before today? Okay, at least one person did. It's always, I mean, it's something, if you watch CBS or all of the other things that do Nova and all of these things, they talk about this a lot too. Okay. Of course, sci-fi people, they take advantage of this a lot, and they write a lot of things in there. And sometimes there is actually more ideas in sci-fi that scientists borrow from them and actually turns out to be correct. So this works both ways. Okay. So the phenomenon of interference occurs for, of course, sound and light, and every single wave varies. This is the idea that I think I talked about, okay, a long time ago when we talked about the interference in this case for the when you have an oil slick, for example, on top of the water, and the waves when they bounce off, okay, in this case they're going to be reflected at different wavelength, and you see the different colors in there, and they come usually out of phase in this situation in here. Okay, this is still the same thing in here. How far we are? Oh man, it's already 5 o'clock and we didn't get into the second topic. Okay, the diffraction grating is many basically slits, not just 2 slits, except now it separates the different colors, because the fact that different colors, that the reflection actually depends on the angle. You cannot do it with the 2 slits, because if you do it with the 2 slits, the colors will spread all over and you have no idea. You will see white everywhere, okay, because the combination, maybe you will see one color here and there. But if you do it with many of them, there's small separation with them, you can clearly see the light being separated. So you will see the different lights of the spectrum. For example, if you shine all the colors in here, red followed by the green, and all the way to the violets in here. So the entire spectrum, you can see it in there. So this device is actually used in spectroscopy to determine what colors you have in there. Of course, if you have a missing color from the original source, you're not going to see it. If there was no green at all, so you're not going to see it at the end. So if you have not a monochromatic light, but more of a combination of certain frequencies or a lot of frequencies, and you run them through a diffraction grating, then you're going to see all the colors of the spectrum develop from the other side. Okay, this phenomenon has to do again with the fact that the refraction in this case depends on the wavelength, because the light that you're seeing from the bubbles in this case actually goes into the bubble and is refracted first and then reflected to you. Okay, so in this case you see the different wavelengths in here. Okay, because during the refraction is when like for example this device, where is it? I saw it earlier here. Okay, this device, you can shine on it. I don't have a spectrum, I don't have a a laser beam in here, but if I do, I turn off the light and you will see it basically refracting inside. Different colors were refracted at different angles. Okay, so this is the same idea in there. I mentioned the polarization when we were talking, I think, about the EM waves, and this is the same idea. So when you have a source of light, and usually the light is unpolarized, it's in all directions, but you run it through a polarizer and it's going to take one direction specifically for the electric field, absorb all of the others, and transmit only one. So that is basically the role of your glasses. Obviously, if you polarize it one way and then you polarize it in the opposite direction, now you have canceled all of the light. It should not come out at all at the end. Okay, so the polarization has to do with the direction of vibration of the electric field. Obviously, you cancel the electric field, you cancel also with it the magnetic field. So it's both of them, because they both have to be together for light to work. This is what we learned from the electric this is the point in here. So she had them in opposite to one another. Now they are actually superposed in the correct direction. Okay. Okay, so you can. Holography, I mentioned it earlier, when you're combining different colors to give the perception of the third three-dimensional universe. I just remembered another point in here, which is really also discussion amongst theoretical physicists and whether or not our universe is actually a two-dimensional universe, and what we see before us, I mean, everything that you see, including your camera, including your phone, including your hand, basically the way it looks, it has a third dimension. It's actually a construct. It's not real. What is real is actually a two-dimensional version of it. So that's actually theory by I think some I forgot his name right now, but the point being, actually there was an experiment, and there is actually an ongoing experiment in New York right now trying to determine whether or not our reality is actually two-dimensional or three-dimensional. This is the hologram, basically, a theory, but it's actually, in this case, it's very easy to understand in terms of how you combine colors and things like that to give you the perception of the 3D. I'm trying to go quickly. I'm relying on you guys that you go and read the content because you're tested on it, okay? If you have any questions, please let me know. I mentioned the light emission earlier. When they have an object that is excited, an element that is excited, it's going to leave its ground state and go to a higher energy level. But then when it's going to go back to its ground state, it's going to go specific from only certain transitions. So each element has its own signature. Okay, so when I look at the spectrum, for an element, I know specifically which element it is. So if I run it through a spectral analyzer that uses, among other things, for example, a diffraction grating, I know what frequencies that it emitted. So I know exactly what element it has. Okay. So again, this is the process. You excite the element, you give it energy, and then now it's excited. Then it's going to release that energy depending on its structure, depending on what it has. Okay, so again, now you excite it. This is the ground state. You excite it, now it moved up in the energy. Then it's going to release a photon, and the excitation in here can be with another photon, or it can be with a temperature or any other excitation that you can think of it, or put it under tremendous voltage. This is actually what we do in the lab. If we're in the lab, we put a tremendous voltage across it so that we excite it, and then we let it emit the light. So that's basically what we do. So put a gas in a big chamber with tremendous voltage. So now it's excited because of the high voltage. And then it's going to emit, it's going to produce light actually for you. Okay. The voltage will produce moving particles, in this case electrons, and this electron will bounce into the inert gas, and the inert gas now is excited, and now is going to emit the lights. The energy of the wave, the gap in the energy of the wave in here between this level and this level, is proportional to the frequency of this beam, to the frequency of the photon. The constant of proportionality is just a number. It's a constant. It's 6.610 to the negative 34. That's a constant. That's Planck's constant. So if I go from this level to this level, this is a big gap of energy versus this level to this level. Okay. This, for example, could be the red color because it's less frequency, whereas this one probably could be the violet. So the violet involves a lot of energy versus that of the red. Obviously, if I go from here to here, probably it's even ultraviolet. Or if I go from here to here, probably it's an infrared. So this is how you think about it. Okay, infrared doesn't actually involve the electrons. Most of the time, it involves the molecules' motions themselves. So which has less energy per photon? Is it red, or is it green? Or is it blue? This is the red, this is the green, and this is the blue. Red, green, and blue. Which one has the less energy or the least energy in this? Red. Okay, very good. Now here is the second question of the day. Rank them in terms of their energy. Rank the red, the green, and the blue in terms of their energy. RGB, okay. So which one has the least energy? Which one has the second least energy? And which one has the highest energy? That's number one. Number two, also in terms of their frequency. So let me write down the question. Rank this light colors, I should say, in terms of their energy and frequency. And lights are green, red, and blue. So that is the second question of the day. Okay, it's easy, isn't it? So the answer, of course, as Kyle has mentioned, the red should have the least energy, the least frequency. The green should have the next, or the higher energy than the green, higher frequency than the green, but less energy than the blue, and less frequency than the blue. Blue has the highest of both the energy and the frequency. It's all because the energy and the frequency, they are basically equal to one another. If you put H equal to 1, of course H is not equal to 1. H is 6.6 times 10 to the negative 34. It's a very tiny number. Okay, so it's not 1. So it's just a number. It's just a fixed number. Planck constant is just a number. Again, I was showing you earlier about basically the prism, and it's used to separate colors actually itself too, similar to how we use the diffraction grating. So you have a light source in here. It goes through basically through focalization using lenses, and then after that, and because lenses actually also to some extent also they use a diffraction, a refraction. So actually there is an aberration. There is a problem with them too. But you would want the beam at the end to come out parallel. And then once it's parallel at the end, you're going to basically separate them, because then you'll have all of the light in one place, of one color in one place and the other colors in a different place. Okay, here is a typical emission spectrum. When you see the entire region is black and only certain colors in it, this is an emission spectrum. So if you work in a laboratory and they show you this, or if you're walking tomorrow to the laboratory and you see the hanging flyer in there, this should indicate that this is an emission spectrum, not an absorption spectrum. Absorption spectrum will be the other way around. It will be all colors and missing some. This one in emission is all basically missing colors and presence. There is some of the colors are present. Okay. Now this is calcium. If you see all of this sequence of colors, all of them, all of these lines, you know that you're dealing only with calcium. So if there is one off, that is not calcium. Same thing in here: strontium, barium, zinc, cadmium, and then mercury. So if you see all of this combination of all of this red, and this is shade of basically, what is it, a different color in here, that is, I can't see it very well in here, then there is the blue, then there's this combination in here. This is not red. This is actually super bright, basically almost to the, I can't see it very well because I can't see the scale in here, honestly. Okay, but this is the signature of these elements. Of course, if we're doing this more accurate in a lab, we'll have a more accurate scale in here. But the point being in here, the lines are specific in here. So the emission spectrum is the presence of these lines. Okay. So this is for the hydrogen. Okay, this is basically the model that he used for the ground state and how the elements are excited and so on and so forth. Now, this law, or the so-called displacement law, is relates to basically what is the color that you see depending on the wavelength. If we look at the sun tomorrow, if it comes up, the sun has this yellowish color. But it has all of the other spectra. If you put it through a spectrum, you see all of the different frequencies, but it maxes around the color blue. I mean, the color Yellow. That is because its temperature and maximum frequency, they are proportional to one another. There is a constant in here, sigma, that connects the two. So if you see a color of an object that is actually white, white is all of the colors, but then it's going to shift one way or the other depending on the frequency. So if you analyze it, you will see where the maximum frequency is. For example, when it's red, when you're starting warming, for example, an object, you put it on fire, it goes from dark to red. That means its temperature is actually maxing in here for lower frequencies, okay? Longer wavelength. But then if you continue heating it, it's going to change color, providing it doesn't melt, because there is a melting point for all metals. So it's going to start to change color toward brighter red, toward orange than you're getting with super high. Now its temperature is even higher, okay? If you get to an area, for example, where it becomes white, that means all of the frequencies are present in here. You can get it, I mean, theoretically, at least, you could get into the blue color. So blue stars, for example, are hotter, a lot hotter. They have higher temperature than our sun. Red stars, for example, like the Proxima Centauri, which is a red star, it has actually its temperature is lower than that of the sun. The big giant star that is not too far from us in here, Betelgeuse, about 500 or 600 light years from us, that is actually lower temperature than the sun, because its temperature is less than that. I mean, its frequency is shifted toward the red than that of the sun. So again, when you see color, you know exactly what's that's exactly what the incandescence also with the light bulbs too. Oh man, we exceeded the absorption spectrum is the opposite, okay? The absorption spectrum, you should see all of the frequencies except some that are missing, okay? Because as light goes through a material, like for example in here, sodium, you will see all of the spectra when you do the analysis except some are missing. Okay, for example, the yellow is missing, so it was absorbed, okay? So again, the fluorescence is related to basically how much light is emitted, and in this case into the ultraviolet light. We have some materials, I think, oh man, I don't know if they are in the lab or not, where we can actually demo this. When we turn off the light, you can see the material basically after you excite it, it's going to be emitting ultraviolet. And this is the principle of low fluorescent light bulbs, basically, for mercury. And phosphorus is similar to basically the lamps. Again, they use the phenomenon of basically Joule heating, because you have a filament in here that reaches tremendous temperature. Remember when we did the electrical circuits, that light, I mean electricity, as it goes through a wire, it increases its temperature. I mean it emits energy, and that energy is actually proportional to the current squared. So when you have the right resistance, in this case, it's going to reach temperature that are so high. And those temperatures, actually, they start to be seen in the visible light. That's how basically the incandescent light bulb works. For the lasers, it's the phenomenon basically is amplified for a similar frequencies, where you get a very high basically output, in this case in the same frequency, and they're all emitted basically in phase, okay? Okay, I think we have covered most of the stuff that I wanted to cover in this chapter, okay? So I will leave the rest of the questions that basically you guys are supposed to be doing. There are a couple of assignments that I need to mention, since I have most of everybody now joined us, at least the ones who are typically attend. The others who come later on. Remember, there were 2 questions, first of all, of the day today. So that's, I hope that you guys caught them. And then also in terms of assignments, we have a quiz and a homework. All of these assignments are due after the break on Monday. That's really the caution that I have to remind everybody. All of the assignment that I am assigning this week, typically the assignments are due after toward the end of the week. Except this time around, it's going to be due immediately because we have a week basically of break. I know you're going to be enjoying your things with your family. Please do not go and visit other people or have people come and visit with you because of this corona that's apparently coming back again. But the point being in here is that the assignment is due on Monday, the 30th of November, immediately after the break, and then we will continue our stuff toward the end in there. So there will be at least another assignment, minimum another assignment this week, potentially two. And again, if they are assigned before the break, they're going to be due in the same time. We still have quite a few content to cover, so I'm hoping that we will get some lead on it this Thursday and then after the Thanksgiving. Okay. Any questions? Let me stop the recording first.